And the next talk is going to be given by Amaia Salvador. Amaia is a PhD candidate at UPC, but it seems like she has not spent a lot of time in Catalonia lately because she's been around the world a lot, going through France, Ireland. She was at the MIT in 2015-16, and over the last summer she's been with Facebook in Montreal. So she will be speaking today about learning cross-model embeddings for cooking recipes and food images. Yeah, yummy.
So Dimo said this title of the talk that I was going to give, so I changed it. So in order to present my latest work, which you'll find that is closely related to what the previous work that I did at MIT about food recognition and understanding. So this is called Inverse Cooking, Recipe Generation from Food Images. So this is work that I developed during a summer internship at Facebook AI Research in Montreal. So this is authored by Michał Drodzal, Xavi Giraud, and Adriana Romero, and myself. So I'm going to start a bit with a motivation of this work on why food, I think, is interesting for us to do research on. So the first thing, I don't think I need to convince you that food is important for us as human beings, right? So we eat all the time. So our lives are very much centered around food, and it takes a very important role in our health and in our social life as well. But perhaps more interestingly, since we're talking about machine learning, computer vision, and multimedia here, or multimodal works, I think that food, especially as food in the context of visual data, so in the form of images and videos, poses a very interesting challenge for us to do research on. So one thing is that food has a lot of intra-class variability, so we find ingredients in many different shapes and colors, depending on the way that they were processed during the process of cooking. And also another thing that I think is interesting is that in order to truly understand food in an image, so when you see an image like that, in order to actually understand what's in there and what composes it, you need to go beyond actually detecting the different ingredients. So the fact that you detect lettuce or you detect tomato, it's not enough to actually understand that that's a salad, and it's not enough for you to say how healthy it is or how many calories it does have. So I think that food, it provides a very good ground for us to develop all these models that go beyond the visible and acquire this high-level reasoning that AI is so interested about. I talked about food a lot, but I especially want to focus on the context of food and recipes, because we're talking about multimodal representations. So this started, 2 years ago. It was presented at CPPR last year. We presented this recipe 1 million dataset, which is composed, of course, of 1 million recipes and 800,000 images for all of these recipes. So not all of them have images, but we have many images for the same recipes. So it's a very large-scale data set, and it allowed us to train deep models to actually understand food and solve tasks such as finding recipes for images. So the first thing that we tried for this task was to design a retrieval pipeline, so what we would do is, we have each sample is composed of a recipe, and the recipe is a set of ingredients and a set of instructions. And then on the other side, we have the image. So what we do is we encode the ingredients and we encode the instructions, and basically we build a representation of the whole recipe, which is fixed length. And then in the other side we have the image, we encode it again somehow, and then we're required to map these two representations into the same embedding space so that it will later, these representations will allow us to retrieve one modality given the other. So this is what we trained at the moment, and so for the code and the models, you can visit this website here, and the data is also available for you to use for non-commercial purposes. So this worked really well in practice, but it has some limitations. So the first thing is that, whenever you pose a problem as a retrieval one, you're constrained to the data set that you have, so you cannot retrieve what's not there, you cannot create anything, and you cannot make a composition of two different recipes. You have either one or the other, you cannot have a composition of both. And also the way that we designed this model, it doesn't allow you to modify the recipe in any sort, so you retrieve the whole thing as a whole, so you retrieve the ingredients and the instructions, and they are tied. This prohibits user manipulation. So here in this example, this query image, it retrieves, so this system retrieved this recipe here. And it does, so it did quite a good job, right? So it's a sushi recipe, but if you look closely, this I think it's a shrimp sushi, and it says that it's salmon sushi. So with this approach that we designed, there's no way for me to remove salmon, replace it with shrimp, and see the instructions affected by it. Well, I could do it, but it should be post-processed, right? So there was no easy way for us to do that. And it's also a deterministic mapping, so for the same image, you always get the same recipe or the same list of ranked recipes from the database. So, so thinking of that, what we propose here is to basically treat the same problem, which is going from the image to the recipe, but instead of posing this as a retrieval problem, we pose it as a generation problem. So now for the image, we're going to generate a brand new recipe for that image. So this is an overview of the model that we designed. So it's made of different components. So the first thing that you do is you get your image, you extract some features. And these features are going to be the input to this ingredient decoder that I'm going to talk about later. But this ingredient decoder is going to provide a set of ingredients that appear in this image, right? And then I'm going to take these ingredients, a set of ingredients that I've predicted, and each of them is going to have an embedding, a representation that is also learned. And then we can reuse the image features, and these two inputs, the pair of image features and ingredient features, are going to be the input to the instruction decoder, which is going to write the rest of the recipe. So each one of the instructions that are required to manipulate the ingredients in order to get what you see in the image. So this is the overview of the model that we proposed. And I'm going to go deep into each one of the components that, well, the ones that are novel. So the first one is the instruction decoder, which is, so this is an autoregressive model that is going to output the recipe, the word of the recipe words, one word at a time. So this is based on the transformer model from the Attention is All You Need paper. So this is based on attention. So the whole model is based on attention. So the first thing, in order to output a word at time step t, you're going to apply self-attention on the previous words that you've predicted. This is a self-attention module here. And then you're going to apply attention on any condition that you have. So in the original paper, they do machine translation. So the condition here would be the sentence in the source language. But in our case, we have two conditions. We have the image, and we have the set of ingredients that we've predicted. So these are the two conditions that we need to somehow put inside the transformer. So we explored several ways of, basically we want to apply attention on both, and we didn't know exactly how because we were dealing with two modalities and not only one. So the easiest one perhaps, and the one that gave us the best results was simply concatenating the two sets of inputs, like considering that they come from the same distribution, you just put them all together and you perform attention on all of them. We tried other things, such as having two separate attention heads for each of the modalities and then merging them, or first attending to one and then the other, or the other way around. But the one that worked best was this concatenation. Then as for the ingredient decoder, so we thought a lot about how to decode ingredients in a way that was proper enough, because there's a lot of discussion that we had regarding whether ingredients are sets or they are sequences. So when you look at the recipe and you read it, of course, ingredients are given as a list, so there's there's a first ingredient and there's a last ingredient, but we thought whether we needed to actually follow this sequentiality that the input data had in order to better predict ingredients, because it's for sure that ingredients have relationships between them. So if I tell you that I'm using salt, it's likely that I'm going to use pepper, but there's no notion whether it's better for me to predict first salt, which then will lead me to pepper, or the other way around. So we take advantage of these dependencies of ingredients, and we reuse the transformer model for predicting ingredients, but instead of applying a loss at each one of the time steps to impose that salt should appear first and then onion, what we do is we output all these probabilities at so softmax probabilities at each time step, and then we pull them across the time dimension so that we end up with a single vector that we can treat each unit as if it were an ingredient classifier and apply a loss on there. So that means that we're taking advantage of the dependencies that ingredients may have, so our model can exploit that, but we're not imposing a certain order in the ingredients. So we have several baselines to compare our model against. We have feed-forward baselines and transformer models that do impose order, and we see that this model that we design works the best, at least for this task of ingredient prediction. So I'm going to finish with some qualitative results. So just to show what our model is outputting at the moment. So this would be one input image that the model would receive. And yeah, I forgot to say that the title is predicted as if it were the first instruction that in the recipe. So that's how we predict it. So in general, we can see that the ingredients that are predicted look reasonable enough. And even it's able to predict or to infer things that are clearly not visible, such as salt, vinegar, or oil, something that you cannot see, but you know that because of what you see, it's likely to have it, so it predicts it. And so, yeah, since we have a large data set, there's a huge variety of different recipes that we can generate. Of course, the model has some problems. It's not perfect. There's the occasional repetition, so it repeats things. Sometimes it forgets things, so ingredients that has predicted and then it doesn't use, or sometimes it uses ingredients that have not been predicted. So there's a lot of work to be done in this field. But so we compared these recipes. I didn't have time to show the numbers, but so far it looks like, according to human judgment in some experiments that we conducted, the recipes that we're able to generate are better than the ones that we were able to obtain using the retrieval model. So it looks like at least we're going towards the right direction. And yeah, so this is all. So if you're interested and want to know more, we have our paper on archive, and code and models will come soon, hopefully. Thank you.